Greetings. In this video, we discuss a very important topic, Fourier transform. Please remember that Fourier series represents a very important mathematical tool for us because Fourier series provided us with the frequency domain representation of any periodic signal x of t. This frequency domain representation shows us the frequency content of the signal x of t, in other words, its harmonic content. And we gain a lot of information from this frequency domain representation. I've shown you an example where we managed to calculate the signal bandwidth from the frequency domain. We can also get a lot of other useful information. For example, we can understand how the signal interacts with hardware systems, such as filters, a very important set of devices, if we know the frequency domain representation of the signal. We can also understand some important signal properties from frequency domain. We can understand how to do some signal conditioning on the signal. We can understand how to transmit the signal on communication channels or antennas for wireless systems, and so on and so forth. You'll probably encounter frequency domain more than once in advanced courses in engineering. The problem though is that Fourier series works only for periodic signals. It does not work for aperiodic signals. So how can we get the frequency domain representation for an aperiodic signal x of t? Here where Fourier transform comes in, because Fourier transform is more general than Fourier series, yet it's quite similar to Fourier series and can show you the frequency content of your signal. Not only that, it works for both periodic signals and aperiodic signals alike. And that's why you'll probably see Fourier transform much more often than Fourier series, because it works for all types of signals. The way we calculate capital X of omega, which is the Fourier transform of the signal x of t, it doesn't matter is your x of t periodic or aperiodic, we do the calculation of the Fourier transform via this equation. Notice that x of omega, which is the Fourier transform of x of t, is equal the integral from minus infinity to infinity of the signal in time domain x of t e to minus j omega t dt. This is the definition of Fourier transform, which you should memorize. Notice that I'm using the complex number j here, and that's why x of omega, the result, the Fourier transform, is in general a complex number. It has a magnitude, the absolute value of x of omega, and it has a phase or angle, the angle of x of omega. Both the amplitude and the phase of this complex number are functions of the continuous angular frequency omega, so they are the frequency domain representation of your signal x of t. By the way, if somebody gives you the Fourier transform x of omega, you can figure out the original signal x of t via the inverse operation, which we call the inverse Fourier transform. The inverse Fourier transform is this integral. Notice that x of t comes from capital X of omega if you apply the Fourier inverse integral, which is the integral of x of omega e to j omega t d omega. And because you're integrating with respect to omega, omega will disappear from here and you're left with time domain t. You get back your original time domain signal x of t. Please don't forget to divide by 2 pi here, unlike this integral which is not divided by 2 pi. Please remember that in many cases, after we calculate x of omega via this integral, we'd like to visualize it graphically. And the way we visualize the Fourier transform capital X of omega is by drawing the magnitude of this complex number versus frequency omega, which we call the magnitude spectrum density of x of t. Notice the word density here. Magnitude spectrum is something we talked about in Fourier series. For Fourier transform, we have a slightly different name, which is magnitude spectrum density of x of t. That's the magnitude of x of omega versus the angular frequency omega. Please also remember that the magnitude spectrum density is always double-sided or two-sided in a very similar fashion to the alpha n's, the magnitude spectrum in Fourier series. Notice, however, that the magnitude spectrum density is drawn versus continuous frequency omega, which gives you a very general diagram enough to include both smooth curves and impulses, which covers both the cases of periodic and aperiodic signals. This is unlike the Fourier series magnitude spectrum, which has only discrete frequency that can only support discrete lines. And discrete lines work nicely with periodic signals, but they do not have support for aperiodic signals. We also typically plot the phase, the angle of x of omega versus frequency omega, and we call this the phase spectrum density. Notice the word density here because it's Fourier transform, not Fourier series. And you'll notice that phase spectrum density is two-sided or double-sided, just like the phase spectrum for Fourier series. For real valued signals, x of t, remember we used to have for Fourier series alpha minus n equal alpha n conjugate. We have a similar relationship for real valued signals x of t in the case of Fourier transform, where we have x of omega equal x conjugate of minus omega. This is, by the way, is something called frequency inversion, which works in a similar way to time inversion, which you're familiar with. This equation, x of omega equal x conjugate of minus omega, tells us that for real valued signals, the magnitude spectrum density absolute value of x of omega has even symmetry, while the phase spectrum density, the angle of x of omega, has odd symmetry. Please remember those two facts when drawing the magnitude spectrum density and the phase spectrum density for Fourier transform. In many cases, especially when x of omega is a real number, we can combine the two diagrams, the magnitude spectrum density and the phase spectrum density, into one diagram, the full x of omega, instead of splitting it into magnitude and phase. To make a distinction, I'm going to call the diagram of x of omega versus omega the amplitude spectrum density. Another thing to keep in mind is that unlike alpha naught, which represents the DC value or the average value of the signal x of t, please remember that the value of x of omega, the Fourier transform at omega equals 0 radian per second, is not the DC value or the average value of x of t. Rather, the DC is represented by an impulse at 0 frequency. So the area of an impulse at omega equals 0, if such impulse exists, is actually the DC value. And if there is no impulse, this means that the DC value is 0. Hopefully, I'll explain this even better when I show you the Fourier transform of a general DC value. Another thing to keep in mind is that even though our spectrum densities are double-sided, there is no such thing as negative frequency in real life. The two sides in the spectral densities show up because we're using complex numbers. And complex numbers are used for our mathematical convenience. We need to understand that in real life, there is only positive frequency, and in our spectral densities, the negative frequencies combine with the positive frequencies to give us real positive frequencies. An important terminology that you will hear a lot when it comes to Fourier transform is the difference between frequency domain and time domain. The two plots we're going to look at, the magnitude spectrum density and the phase spectrum density, are what we call the frequency domain representation of our signal x of t, because they show the frequency content distribution for that signal. So they represent an alternative but equivalent way to look at our signal in contrast to its time domain representation. We say the signal was transformed from time domain to frequency domain using the Fourier transform operator, and it is transformed in the opposite direction from frequency domain to time domain using the Fourier inverse operation. But please understand, even though we make a distinction between time domain and frequency domain, and we say we're transforming from time domain to frequency domain or frequency domain to time domain, we're actually just looking at different views of the same exact signal. It's like we have one object, but we're looking at that object from different perspectives. If you look at the signal x of t as a description of time, we say this is time domain. But if you look at the frequency content of the signal x of omega, we say this is the frequency domain. And the Fourier transform takes us from time domain to frequency domain, while the Fourier inverse takes us from frequency domain to time domain. Also, please understand that the transformation between time domain and frequency domain is unique. is 1 to 1. Hence, x of omega represents a unique description of the signal x of t. And knowing the spectral density is x of omega, we can reconstruct the signal x of t via Fourier inverse. To illustrate this uniqueness, this 1-to-1 mapping, we say x of t and x of omega represent a Fourier transform pair. And we write it like this. We say x of t corresponds to x of omega and x of omega corresponds to x of t. They are two representations that are equivalent for the same signal, for the same thing. Alright, so you understood that if you want to find x of omega from x of t, you need to do this integral. And we're going to go through some examples in the next video. But what should you expect from this integral if the signal is periodic or if the signal is aperiodic? In the case of periodic signals, the Fourier transform x of omega for the periodic signal x of t is almost identical to the Fourier series complex exponential form alpha n of that same periodic signal x of t. So if you found alpha n, the complex exponential Fourier series, you already found the Fourier transform x of omega. Please remember that they both have similar integrals and both give you complex numbers. However, there is a slight difference, and it's very minor difference. We can easily prove that for periodic signals, we can convert the Fourier series, the complex exponential form alpha n, to Fourier transform x of omega by introducing only two modifications. The first thing you want to do is multiply each alpha n value by a factor of 2 pi. And then the second thing to do is convert each discrete value alpha n, which was represented as a line in the Fourier series spectrum, into an impulse with area of 2 pi alpha n in the Fourier transform spectrum density. The proof is very simple, especially if you use Fourier transform properties. But I'm going to keep that for a later video. Rather than going through the proof right now, let me show you a simple example, because I think an example will make you understand the idea way better. Remember this signal x of t repeated rect. We managed to find the Fourier series for that repeated rect. Turns out that the alphas, the Fourier series complex exponential form, are controlled by a sink. And we draw the double-sided amplitude spectrum for this repeated rect as those lines which are enveloped by a sink. If on the other hand, now you evaluate the Fourier transform of this x of t using the integral I've shown you, here is what you're gonna get. You're gonna get this amplitude spectrum density x of omega, which looks very much like the Fourier series. However, notice that instead of each line, I have an impulse at that location, and the values are not alpha naught, alpha 1, alpha 2, rather they're multiplied by 2 pi. So you're gonna get 2 pi alpha naught, 2 pi alpha 1, 2 pi alpha 2, 2 pi alpha 3, and so on. Otherwise, both answers look very similar. To show you the result even better, let me show you the amplitude spectrum and the amplitude spectrum density next to each other. Here is the double-sided amplitude spectrum, the Fourier series, for my repeated rect. This is the amplitude spectrum density, the Fourier transform of the same repeated rect. Compare this answer with this answer. They are almost identical. Both are double-sided. There are only two differences. Notice that each alpha here is multiplied by 2 pi in the Fourier transform. Another thing is that those lines are replaced by impulses. The area under the impulse is 2 pi alpha 1. The area under the impulse is 2 pi alpha naught. The area under the impulse is 2 pi alpha minus 1, and so on and so forth. So why is it that for periodic signals, the Fourier series and Fourier transform look alike? The reason is that periodic signals are actually the sum of an infinite number of sinusoids, and each sinusoid is equivalent to 2 impulses in Fourier transform. That's why you're gonna get infinity impulses corresponding to infinity sinusoids. Plus, of course, the impulse around 0, which represents the DC value. In conclusion, usually I do not evaluate Fourier transform for periodic signals. Rather, if I am faced with a periodic signal x of t, I find the corresponding alpha n, the Fourier series. We already practiced calculating Fourier series alpha n, Not only that, sometimes we have the answer for Fourier series in the trigonometric form or the compact form, and we can easily convert that into the complex exponential form. Once you have the alpha n's, you can easily modify such alpha n's to get the result of the Fourier transform x of omega. Just multiply by 2 pi and convert the lines into impulses, and you're done. Good. That was periodic signals. You already know how to calculate Fourier series, so it's very simple. But for aperiodic signals, we do not have Fourier series. We have to calculate the integral to find the Fourier transform x of omega. However, it's still very simple. Why? Because the Fourier transform x of omega of the aperiodic signal x of t looks quite similar to the envelope, which means its continuous frequency smooth curve of the Fourier series complex exponential form alpha n of the corresponding periodic signal repeat x of t. So if your x of t is aperiodic, but you create a repeated x of t periodic signal, your aperiodic signal will have a Fourier transform that looks very similar to the envelope of Fourier series of this repeated x of t. Don't worry if you don't understand this completely. I'm going to show you an example in a second. But I want you to appreciate and understand that your skills in calculating Fourier series will translate equally well to Fourier transform. Why? Because the calculations of Fourier series alpha n, which require this integral, look very similar to the calculations of Fourier transform, which require this integral. Let's compare the integral for x of omega, which is the integral minus infinity to infinity x of t e to minus j omega t dt, with the integral for alpha n, the complex exponential Fourier series, which is 1 over t naught integral over 1 period t naught x of t e to minus j and omega naught t dt. Please notice how similar this integral to this integral. You have x of t here, you have e to minus j here, but instead of omega, which is continuous angular frequency, you have a discrete angular frequency here and omega naught. That's one difference. Another difference is that you divide by t naught, the fundamental period here, because the integral is over one period. Here you don't divide by t naught. Hence, those are the two differences you'll start noticing between Fourier transform and Fourier series. There is an extra t naught in periodic signals that you will not see in aperiodic signals. And also, instead of discrete frequencies and omega naught, you'll end up with continuous frequency omega and smooth curves for aperiodic signals. However, the results are quite similar. Let me show you an example so you can understand my argument. Let's take this example. X of t is repeated rect. We found Fourier series for this periodic signal. This is periodic. We found the alphas, alpha naught, alpha 1, alpha 2, alpha 3. That's Fourier series. For Fourier transform, the conversion was so easy. I multiplied by 2 pi for each value here, and I converted into impulses. Notice though that the envelope, which is this smooth sync signal, is still the same between Fourier series and Fourier transform. It did not change. It's still controlling the alpha n values. What if now you consider x of t as this aperiodic single rectangular shape? Instead of repeated rect, now you consider one rect, and you do the integral to find x of omega. What is the answer you're gonna get? You're gonna get this smooth curve sync signal as the answer for the Fourier transform x of omega of this aperiodic signal. Let me put the two curves next to each other. Notice that this is the Fourier transform similar to Fourier series of repeated rect, and this is the Fourier transform of just one rect. This is aperiodic and this is periodic. This is periodic and this is aperiodic. What is the difference? One is discrete impulses at omega naught, 2 omega naught, 3 omega naught, 4 omega naught with an envelope that is sync. The other one, Fourier transform of aperiodic, is a smooth curve that is sync. Not discrete, not impulses, rather a smooth curve. We'll do some examples, including this rectangular shape, and you'll see that this is the correct answer. So the message is Fourier transform is very close to Fourier series, complex exponential form, and your skills in calculating Fourier series will translate easily to calculating Fourier transform. But the nice thing about Fourier transform, it has answers for periodic signals and aperiodic signals. It's not limited to periodic signals. Not only that, if you do Fourier transform and you find x of omega for periodic signals, it looks very much like Fourier series. If you try to find x of omega for aperiodic signals, you're also going to get an answer, but Fourier series is incapable of doing that. In the next video, I want to go through some examples and we want to calculate the Fourier transform of rectangular shape and show you that it is actually sync. But I'm going to avoid solving examples for periodic signals, because for periodic signals, just find the Fourier series and convert that into Fourier transform. See you in the next video. If you have any questions, leave them in the comment section. This is Muhammad Hawa. Goodbye.